Yes, okay. So, hello everyone. I'm Ariane Nicolas. I'm a first-year PhD student at Inria Rennes. And today I'm going to present you the paper on the origins of indirect jumps in embedded software, which I co-authored with Isabelle Puaut, Erven Rohou, and Ronan Lashermes. So, embedded software often need to provide guarantees regarding correctness, execution time, or security. Most of the time, these guarantees rely on the presence of a control flow graph of the program, which is the graph representing all possible execution paths of the program. So here you have an example of a source code and the associated CFG. So CFG is used, for example, for data flow analysis, worst case execution time estimations, or control flow integrity mechanisms. So in order to provide solid guarantees for embedded software, the control flow graph must be accurate. That means it must faithfully represent all possible execution paths and avoid infeasible edges. In a CFG, we encounter in general two types of control flow transfers. Direct jumps, whose target is statically known. So here you have an example of a direct jump in RISC-V assembly, coming from a function func1 and going to a label 1. So here the associated CFG is fully accurate because we know exactly where to go. The second type of control flow transfer is the indirect jump. So this time, the target address is stored in a register. That means it will only be determined at runtime. An indirect jump may have multiple possible destinations depending on runtime data, and its target may even be completely impossible to determine statically, for example, if depending on user input. So consequently, in the general case, constructing an accurate CFG in presence of indirect jump is impossible. So in this work, we are interested in indirect jumps' origins. We try to answer the following research question: when and why are indirect jumps generated by the compiler? Are they due to programming constructs used by the developer, or are they directly generated by the compiler, maybe without the developer knowing it? Some other questions arise also. Are there differences between binaries from different languages? What is the impact of optimization levels on indirect jump generation? So to answer these questions, we provide the two following contributions. First, a fine-grained classification of indirect jumps' origins, gathering programming constructs and compiler transformation responsible for their generation, and a systematic empirical study on indirect jump distribution in binaries from multiple programming languages, compiled with two different compilers at multiple optimization levels. So before going deeper into the presentation of these contributions, I must first of all introduce the architecture we are working on, which is RISC-V. So RISC-V is an instruction set architecture which is open and extensible. We chose it because of its increasing adoption in embedded systems. So RISC-V provides 32 general purpose registers from X0 to X31. And for our work, some of these registers are relevant to know. So the 0 register is hardwired to 0. The X1 or RA register is dedicated to the return address in case of a function call. And the T0 register may be used as an alternate return address. So RISC-V provides a unique indirect jump instruction, which is JALR for jump and link register. This instruction takes as argument the return address and jump to the address contained in the RS1 register, plus or minus an offset. So depending on the value taken by its argument, this instruction may have multiple different behaviors, or 4 different behaviors, that are defined by the ABI convention of RISC-V. So if the return address is properly set, we want to come back to the calling point, so we know it's an indirect call. On the contrary, if the return address is set to 0, we want to jump without returning, it's a plain indirect jump. If the target address is the return address, then it is a function return. And finally, RISC-V provides a 4th type of indirect jump, which is generated when a direct jump cannot reach its target. Instead, a direct jump is generated, preceded by an AOIPC instruction to construct a complete address. So now that I have presented RIS5, let's dive into our first contribution, the detailed classification of indirect jumps origins. So as said just before, RIS5 specification allows to differentiate 4 different macro categories of jump. So indirect calls, returns, long-run jumps, and indirect jumps. Some of these categories can be detailed to further refine the origin of the jump. So here is the complete classification. I will detail a few of these categories in the next part, but for now, let's focus on this big picture. So some of these categories are due to the compiler. It's the case for returns, long-run jumps, dynamic linking calls, jump tables, and tail calls. The others are due to the developer, so namely dynamic dispatch, function pointers, callbacks, and computed gotos. So now I will present 3 selected categories of jump. Jump through dynamic dispatch, long-run jumps, and jump tables. So the other categories are detailed in the paper if you are interested. So first of all, jump through dynamic dispatch. This category of jump was present in 2 of the studied languages, C++ and Rust, and is due to programming construct used by the developer. So in these 2 languages, the concept of polymorphism allows to define abstract interfaces which can be implemented by multiple concrete types. So here is a snippet of C++ code. Here we define a base class which contains 2 virtual methods, method 1 and method 2, each of them printing a small message. Then we define a derived class which inherits methods from base class, and it overrides the method 1, now printing a different message. Then we define a call method 1 function, which takes as argument a base reference. So here, the polymorphism allows to give as argument either the base class itself or any class inheriting from base. So that means we don't know which exact class will be given as argument at runtime and which exact method 1 will be called. So this is determined at runtime through dynamic dispatch and through the use of a virtual table. So for each object, the compiler will generate a virtual table, which is an array containing pointers to each declared methods. So here for a base object, we have an array pointing to method 1 and method 2. Then when a class overrides a method, the pointer will be updated to point to the new method. Here for a derived object, method 1 points to the new method 1. Then at runtime, the vtable of the object will be read and an indirect jump will be performed to the right method. Okay, so now I'm going to present long-run jumps. So in RIS5, we have a direct jump instruction, which is JAL, and this instruction can reach targets in a range of plus or minus 1 megabyte from the current PC. If the target is farther, the compiler must generate a long-run jump. So it takes the form of a fusion of 2 instructions, AUIPC and GILR. So AUIPC constructs the higher bits of the address, and GILR constructs the lower part of the address and performs an indirect jump. So here we can notice that even if we have an indirect jump, the address is statically known. So it is a special type of indirect jump that is specific to fixed size ISA. Now jump tables. So jump tables are generated by the compiler to optimize long comparison sequences, such as switch statements or large if-else sequences. So here you have an example of a snippet of code of a switch containing 3 cases. So a jump table is an array containing the addresses of each case code blocks of the switch. So here for this code, the following jump table is generated, pointing to the 3 cases code blocks. Then at runtime, the switch input will be used to select which case code blocks to jump to, resulting in an indirect jump. Okay, so here it is for the 3 categories I presented. Now let's go to present the second contribution, which is our quantitative study on indirect jump generation. So the objective of this empirical study is to quantify the number of indirect jumps generated in RISC-V binaries and precisely the proportion of jumps in each identified category. We want to highlight the differences between binaries from different languages and the impact of optimization levels. So I will not present the latter here because of the timing. Okay, so to obtain binaries, here is our experimental setup. As said before, we target a RISC-V architecture and precisely a RISC-V 32G architecture without compressed instruction. So we studied 4 different languages, C, C++, Fortran, and Rust. We used the Spec CPU 2017 benchmarks for C and C++ and Fortran languages and added to it the glibc. And for Rust, we made our own small suite of benchmarks using ripgrep, core utils, and cargo. So we compiled these benchmarks using 2 compilers, GCC and LLVM, at 6 different optimization levels. Then, once the binary were compiled, we disassembled them and performed static analysis on the disassembled code. The idea is to, for each indirect jump instruction, to obtain its category. So we have different levels of identification. Some categories of jump can be identified directly from RISC-V ABI, depending on the value taken by the registers. So it's the case for returns and long-run jumps. Then we perform backward analysis on instruction preceding the jump to identify recognizable patterns. So at this level, we can identify calls through vtables, tail calls, and dynamic linking calls. Then, if the disassembled code doesn't give any hint on the category, we obtain the source code line using address to line, and we perform pattern matching on it. So at this level, we can identify function pointers, jump tables, and computed gotos. Then, if some jumps are left unclassified, we can perform a manual pass to identify the category manually, but this pass is optional. So here are the results we obtain after our empirical study. So on this graph are displayed benchmarks compiled using optimization level 02. So benchmarks are separated by language and ordered by size. Here are the smallest benchmarks and the largest benchmarks this way. The histogram bars represent the proportion of indirect jumps in each category over the total number of instructions. So I'm going to present the key insights on this graph. So first of all, we can see that the overall proportion of indirect jumps is quite small, only up to 8% of the instructions in Rust benchmarks. Then we can notice that smaller benchmarks exhibit less diversity in different categories of jump. This can be explained because larger benchmarks require more abstractions and thus more indirect jumps. Larger benchmarks exhibit a higher percentage of long-run jumps. This is expected because as the binaries are bigger, direct jumps are more likely to be too far from their targets and to be replaced by long-run jumps. We encountered that it's especially the case in Rust benchmarks. We encountered that it was due to its linker, which by default generates for every call a long-run jump. This can be disabled using a specific option. In C, we can see that there is a quite specific systematic use of function pointers. We encountered that it was mostly function pointers stored in structures to serve as methods for the structs. And in C++, we can see that there is a wide use of dynamic dispatch calls, which is expected also because of the object-oriented paradigm of the C++. Okay, so here it is for our results. I will now conclude and open on future works. So I presented here our work on the origins of indirect jumps. We provided 2 contributions, a complete classification of indirect jumps origins and statistics on the number of indirect jumps generated in each category in RISC-V binaries. So now that we have identified the different categories of indirect jumps, future works could focus on how to manage them in embedded software. So development guidelines could be formulated to discourage the use of certain programming patterns or to encourage the use of specific compilation options to remove some categories of indirect jumps. And to go even further, a more radical approach could think about entirely removing the indirect jump instruction from an IRISA and providing compiler and hardware support to efficiently replace them with safer constructs. So this is the approach that I will be exploring during my thesis. So thank you for your attention. Feel free to ask a question.
Are there any questions? Can you?
Yeah, hi, thanks for the talk. Kind of a small question. So when you say tail calls in the paper, I guess you mean as in like tail call optimization?
Yes, tail call optimization, yes.
Why does that lead to indirect jumps? I would have expected it to be basically like, you know, a while loop where you just kind of jump back to the beginning of the function each time.
A tail call is, I mean, at the beginning it was supposed to be an indirect call at the end of a function, but it is replaced by a jump because it's the last instruction of the function. So you don't need to return to the calling point. It's only a jump which is performed. Does it answer your question?
But then in that case, there would be no indirect jump at the end of the day, right? Or
no, the call at the beginning was supposed to be an indirect call. So it's replaced by an indirect jump instead of a call.
I think the question is, if it's a tail call, there shouldn't be. It should be a direct jump and not an indirect one.
Yes, but the indirect jumps are generated only when the last instruction was supposed to be an indirect call and not a direct call. A direct jump will be generated as a tail call, as an optimization, if the call at the beginning was a direct call. But here it's indirect calls that are optimized as indirect jumps.
Okay, thanks.
Okay.
Yeah, about the radical.
Yeah.
Go back one slide, right?
Yes.
So I think removing the instruction is quite radical, but
yeah.
You could still enforce compilers to generate zero constructs, or you could, like, instead of going and finding that in the assembly,
yes.
like for instance the switch case thing. So there's a lot of cases where the compiler could produce
something
extra
else.
debug information, something because what the interest is to be able to reconstruct more accurate CFGs.
Yes, exactly.
So if this information is known by the compiler, because it is known, so this can be passed somehow, so that the control flow graph can be more accurately produced.
Yes, but there are some kinds of indirect jumps that are more difficult to replace with something else.
Yeah, no, that part I know, but I'm saying that you could increase the accuracy of the control flow.
Yes, of course. That's why there could be development guidelines to.
No, but with the compiler as well.
Okay.
So the compiler could help out in.
Yeah, yes. The compiler itself could.
Hi. Thanks for this analysis. Two questions. First of all, C++ supports lambda. Did that appear at all in this analysis at all?
So we used the spec CPU 2017, and we encountered that there were no lambda at this point. But I think, yes, it would be an indirect jump.
Okay. Other question is, Rust has function blocks a lot like lambdas, and they use them a lot. I guess those show up in the analysis.
Yes, you can read the paper if you want, but yes, but this kind of jump, it depends if they are under a trait, if they are given as argument, like you speak about closures, that's it. Right. Yes, closures can result in an indirect jumps if they are given as argument in a function.
Thank you.
In your presentation, you only use 32-bit instructions. Have you looked at applications with different bit widths? 64 bits, 128 bits?
I think 64 instead of 32?
Yeah.
I think it normally doesn't change anything. It's only the addressing that changes.
But it would be interesting to see whether the analysis you have done would be
maybe.
The same or would become different.
yes, for example.
Yeah, for example.
I have a question as well. So you mentioned you are using a static analysis.
Yes.
Could you tell us why you need you need to perform the analysis at the source code and at the binary level as well? So why do you need both, and what do you do with this analysis?
We wanted at the beginning to do only static analysis on the binary, but it was we were missing information, so we continue at the source code level. We could have used only the source code maybe, but yes, it was also to see if some specific patterns were generated in the assembly. So both were interesting for us.
Okay. Okay, so let's thank the speaker again.